Hello, and welcome to tonight's example. Tonight I'd like to do an example of a thermochemistry problem that involves limiting reactant stoichiometry and the ideal gas law. Let's take a look at this problem. Determine the amount of heat released by the combustion of 5 liters of acetylene gas, C2H2, at 3 atmospheres and 25 degrees C with 4 liters of oxygen gas at 2.5 atmospheres and 27 degrees Celsius. We're given a balanced chemical equation which tells us for every 2 moles of acetylene gas, we require 5 moles of oxygen gas to produce 4 moles of carbon dioxide gas and 2 moles of liquid water. The change in enthalpy for the reaction, aka the heat released for the reaction, is 2,599 kilojoules. The negative sign is telling us this is an exothermic reaction. Heat is being released. So this is a thermochemistry problem because we're dealing with heat being released as a product. It is a limiting reactant problem because we're given the volume, the temperature, and pressure of both of the starting gases. This means that one of them will run out before the other, limiting the amount of heat being produced. I can tell that we can solve for moles because using the ideal gas law, PV equals nRT, I can solve for the moles of the oxygen gas and the moles of acetylene because we have all of the other variables, pressure, temperature, and volume. Before we even start solving for the number of moles, I want to generate the thermochemical relationship between the stoichiometry of our two reactants and delta H. So let's take a look at the coefficient in front of acetylene. It tells us for every 2 moles of acetylene, I will produce 2,599 kilojoules of heat. So that is the ratio of the acetylene from the balanced chemical equation to delta H. What about the relationship of the oxygen? Well, for every 5 moles of O2 from the balanced chemical equation, I will also produce 2,599 kilojoules of heat. So those are the stoichiometric relationships that I'm going to need to solve for heat. What about the moles of the acetylene and the moles of the oxygen? I'm going to use the ideal gas law to solve for both of these. Let's start off with the acetylene, C2H2. I'm rearranging the gas law, the ideal gas law equation, so that we can solve for N. Remember, the ideal gas law is PV equals nRT. Rearranging to solve for N, the moles of gas, I have PV over RT. From the information in the problem, I know that the pressure of the acetylene is 3 atmospheres. The volume is 5 liters. R is 0.08206 liters times atmospheres divided by moles times Kelvin, gas law constant. And the temperature must be converted into Kelvin, so 25 plus 273 gives me 298 Kelvin. And when I plug this into my calculator, I got 0.613 moles of acetylene. Now I'm going to take that moles of acetylene and use the ratio that I generated previously. So 0.613 moles of acetylene. I'm going to multiply that by the fact that we generate 2,599 kilojoules of heat for every 2 moles of acetylene used. That is from the balanced chemical equation and its relationship to delta H. And what I calculate out now is the amount of heat released by exactly 0.613 moles of acetylene, and that's going to be 797 kilojoules. Again, negative because this is exothermic. What about the oxygen? Well, solving for the O2, rearranging our gas law, N equals PV over RT, I can now solve for the moles of oxygen. Plugging in the information from the problem, the oxygen is at 2.5 atmospheres. There are 4 liters of the oxygen gas. Divide that by 0.08206 liters atmospheres moles Kelvin, and multiply that by the Kelvin temperature, which is 300. I got that from adding 27 to 273. And the number of moles I got for the O2 is 0.406 moles of O2. Multiplying that by the thermochemical relationship from the balanced chemical equation, 0.406 moles of O2 multiplied by the fact that for every 2,599 kilojoules of heat released, it required 5 moles of O2 from the balanced chemical equation. Moles of O2 are going to cancel, and once I do the math, I got negative 211 kilojoules. Because this is a smaller amount of heat being released, we can clearly see that the amount of heat being released is dependent upon the O2, which is the limiting reactant. I hope this example helped you. Thank you.